Hello, I am Aditya Gulati and today I would be covering discriminative versus generative classifiers. In this lecture, we would be covering basics of vector graphs, then one generative model named naive-Bayes classifier, then one discriminative model named logistic regression, and then we would try to cover trade-offs between discriminative versus generative models. The prerequisites for this lecture are going to be basics of probability like Bayes rule and marginalization, then some functions like sigmoid, and then some very popular distributions like Bernoulli and normal. Now consider a machine learning classification problem in like a very popular data set I am going to quote here, spam classifier data set. So in this spam classification problem, let us say we have one observed variable x, which are the features. Now we can classify any mail into spam or non-spam given by the target variable y, 0 and 1. The features of this particular email can be the words, whether some particular word has occurred or not. Let us say the word bank, account or zoo. Now given this data set, we would now model this problem. Now if we are modeling this classification problem, we essentially want to know p of y given x. Given all the features, what is the probability of some target variable y, whether it's a spam or non-spam. To do this thing, consider this. Let us say the features x are conditionally dependent on the target variable y. Such kind of classifier is a generative classifier. Now the opposite case, the target variable y is conditionally dependent on features variable x. Such kind of model is a discriminative classifier. Essentially both of these model the same thing, but in case of discriminative classifier, we can directly model it as p of y given x. The reason being that y is directly dependent on x. But in case of this generative model, we would utilize the power of Bayes rule and model this as p of y given x equal to is directly proportional to p of y into p of x given y using the Bayes rule, prior and posterior. So such kind of models are generative in nature. Now we can extend this model to more number of features x1 to xn. Let us say all these features are dependent on each other. So a generative model would be written like a vector graph like this without any loss of generality, whereas for discriminative classifier it would be like this, the right one. Now in this case, we can see that all features are dependent. In case of generative model, all features are dependent on the target variable. Whereas in case of discriminative model, the target variable is directly dependent on all the features and all the features are dependent on each other. Now let us go through one algorithm called naive-Bayes. Now in case of naive-Bayes, let me lay out an assumption here. The assumption is that any of this node xi is conditionally independent of any other node, let us say x minus I, any other node than I given y. Essentially it boils down to this, that given the target variable, all the features are independent of each other. So our vector graph would be summarized like this, that all these connections between these features would go away. So this would be our vector graph for naive-Bayes classifier. Now if we want to model this, we can use the Bayes rule, the one that I have highlighted before, prior into posterior. So this can be written as, we essentially want to know, given x1 to xn, what is the probability of p of y equal to 1, given these variables. Now utilizing the properties of Bayes rule and this vector graph, this can be written as p of y equal to 1, the prior of this node, and all the conditionals p of x1 given y, x2 given y till xn given y multiplied by each other, given y equal to 1. This is divided by the normalization constant, which is equivalent of scenario where y is equal to 0 and summed with scenario where y was equal to 1. Now this is a naive-Bayes classifier. This is a type of generative model. Now let us learn a discriminative model called logistic regression. Think like this. In discriminative model, like let us say I would be covering logistic regression. The most simple way here to model y using all the xi's would be to learn a linear classifier on top of it. So a linear model of all these x's would be equal to y. So in such scenario, let us say I would like to learn a linear model on this. So this can be written as w naught plus summation of wi xi. Let us say we write z as follows. But now the problem here is that z can take any value from minus infinity to plus infinity given the weights. So we would like to constrain it to 0 and 1. No matter what happens, I want it to be constrained between 0 and 1. So we can utilize this function sigmoid and we can use sigma of z, and we can essentially write this as 1 plus e power minus w naught plus summation of wi xi. So you can use this as the prediction and compare it with the target y, and you can run a very simple optimization optimizer like stochastic gradient descent or any other optimizer to obtain these weights and learn a discriminator here or a classifier here. So this is the logistic regression. Now note that, let us take the two assumptions here. Now the main key assumption of a naive-Bayes classifier is that all the sibling nodes are independent of each other given the parent. Let us highlight this as A1. The key assumption in case of logistic regression is that in the end it follows the form of 1 upon 1 plus e power minus something, and this is called as, let us say, logistic form, and highlight it as an assumption 2. We have two assumptions here for generative and a discriminative model. Now what if I tell you that under some circumstances A1, this assumption, can imply A2, this assumption? How? So let us say that our priors are modeled as Bernoulli distribution and our posteriors are modeled as normal distributions. These are modeled as normal distribution and this is modeled as Bernoulli distribution. If we fit in these equations here into this, then we would obtain a logistic form. Now this is a very strong statement that I am making here. These equations fit into this would be equivalent into a logistic form. With respect to time, I won't be covering this derivation, but it's very easy to as a plug and play kind of formula here and derivation here. So I won't be going through that here, but given what I said right now is correct, A1 would imply A2. Now I can make an even stronger statement that if some distribution is explainable or is able to be modeled in case of a naive-Bayes classifier, then it would follow a logistic form. So something like Bernoulli and normal fitted into this would end up into a logistic regression. So I can say here that A1 would imply A2, and naive-Bayes performance is a subset of logistic regression performance in such scenarios. So if we have large amount of data, let us say number of data points is large, we know that from law of large numbers, prior would follow a Bernoulli and these conditionals would follow a normal distribution. Now in such scenario, given n is more than infinity, logistic regression would perform at least as good as naive-Bayes classifier. So this is again a very strong statement that I have made here, given that we have large amount of data. This shows that discriminative models like logistic regression, decision trees, SVMs are really powerful in nature. We can see here the number one reason being that in case of a discriminative model, the features are dependent on each other. There is no such assumption that was made in naive-Bayes classifier. So this is one of the key reasons why discriminative model is very powerful here. Number two thing is, let us consider a scenario in which x1 is equal to x2. I would say how. Let us assume that in our training set, in all of the emails, the word bank occurs with account and nowhere else. So I can say here that that there are two scenarios, either x1 is equal to 1 and x2 equal to 1, or x1 is equal to 0 and x2 is equal to 0. Either they occur together or they don't occur together. Let us say this is just an assumption here. Now in case of a naive-Bayes classifier, these both probabilities would be modeled, and this is called as double counting the evidence. Whereas in case of a logistic regression, there would be a learning that these two features are redundant to be learned together. So one of the feature would be required by us, hence the weight of one of these features, either x1 or x2, hence either w1 or w2 would be equal to 0. And this is what is learned by logistic regression, which shows its efficiency, that this is a more efficient kind of algorithm in terms of learning the correct features. Now we have shown the powers of discriminative model. Would we say that discriminative models is the only thing? Definitely not. Generative models are powerful enough in many scenarios. All these discriminative models rely on the assumption that all these x's are observed in real in our data set, that all these variables are really observed, but that never happens in the real world scenario. Many of these variables would be unobserved, and we won't be able to model any such logistic regression classifier on this thing. Whereas in case of a generative model, we can utilize the property of marginalization to cut out some variables and utilize only those which are observed, called as evidences. So in such scenario, generative models are more powerful than discriminative models. So in and all, we can summarize here that which one to use, discriminative model or generative model. We can summarize here that it is dependent on your problem. We need to understand model our problem, model our data set more, and then further know that which of these models would be useful for us. So there is no golden rule, no golden algorithm that works for us. It is all dependent on your trade-offs and what your motive is. So with this, we have summarized discriminative versus generative classifiers. Hope you liked the video. Feel free to drop me an email on adgulati@ucsd.edu, given in the description as well. Thank you very much. Thanks for watching.